All right, today's lecture is going to be about molecular polarity. We've already talked about individual bonds. Individual bonds, remember, can be polar or nonpolar, and that depends on a difference of electronegativity. Okay, so we know if they are further apart on the periodic table, then they have a large electronegativity difference, and that makes them polar. One of the atoms can pull the electron density closer to its nucleus and making a polar bond. In general, molecules, though, can also be polar or nonpolar, and this is due to the shape. So if the shape, all of the atoms are the same, so they are symmetric around the central atom, and there are no unshared pairs of electrons, you will have a nonpolar molecule. If all of the atoms are not symmetric, meaning they are different and they have a different electronegativity around the central atom, or they have lone pairs, then you tend to have a polar molecule. Okay, a polar molecule. Polarity comes down to the shape, okay, and where the electron density is. And that electron density can give an overall dipole to a molecule. And so if we look at carbon dioxide is nonpolar. Why is it nonpolar? It does have polar bonds. Okay, so look here, we can see that there is a difference in the electron density. It is pointing out towards those oxygen. So we have two polar bonds, but because they are opposite each other, they cancel and the overall molecule is nonpolar. If we look at something like water, water has our two lone pairs up at the top. We know those lone pairs require a lot of space, which squeezes the angle. We know that we have a dipole still towards the oxygen, but the shape does not cancel those dipoles out, so we have an overall dipole moment. So there's a little flow chart you can use for polarity. First, you want to say, is it covalent or is it ionic? Okay, remember ionic is a metal and a nonmetal that come together, or a metal and a polyatomic, but we have a cation and an anion. And this is a complete separation of charges. Okay, so this is a transfer of electrons, it is a separation of charges, and we have ions that break apart in solution. But for covalent, we want to look to see then is it polar. Okay, so are the bonds polar? If the bonds are polar, then you have to continue through the flow chart. If you say no, the bonds are not polar, then the molecule itself is also nonpolar. You must have polar bonds to make a polar molecule. Then you're going to look at the average position of the partial positive and the partial negative. That is, does the overall dipole cancel? Does it equal 0? Okay, if it cancels, then it is nonpolar. Okay, when we look at polarity, again, we have nonpolar. This is trigonal planar. Okay, trigonal planar has 120-degree angles, and they're each pulling in opposite directions. Notice we have a central atom, and all of the atoms around the central are the same. There are no lone pairs, so it's nonpolar. Same thing with CCl4. We have a central atom, and the 4 atoms around the outside are nonpolar, or are polar bonds, but they are arranged in a symmetrical way, so it's an overall nonpolar molecule. Predict whether these molecules are polar or nonpolar. So we're going to have BrCl. This has a difference in electronegativity towards the chlorine, and so therefore it is going to be polar. For SO2, we can draw many different Lewis structures, but one of them that we draw is going to look like this. Because we have a lone pair, even though we have two dipoles that look like they're going to cancel, that lone pair is going to also make it polar. When we look at SF6, it is octahedral, okay, and octahedral with all of the same atoms around the central with no lone pairs is nonpolar. Okay, and these slides go through that answer. Now, hybridization. This is the other thing we really haven't talked about. Hybridization is when we take our s orbitals and our p orbitals and our d orbitals and we mix them together to make a hybrid orbital. Okay, so in valence bond theory, electrons of two atoms begin to occupy the same space. This is called overlap, and this overlap is what creates our bond. Okay, the sharing of space between two electrons of opposite spin results in a covalent bond. Okay, that's where we're getting our covalent bonds. Increased overlap brings the atoms together until a balance is reached, and this is our intermolecular distance. Okay, so our perfect intermolecular distance is where the bond is created. In this one, it is 0.74 angstroms, and it has an energy of negative 436 kilojoules per mole. All right, so that is our sweet spot here. Hybrid orbitals form by mixing. So think of putting your S, your P, and your D in a blender, and what comes out. Okay, these new orbitals have equal energy and are called degenerate orbitals. Okay, and this is the process of hybridization, which is the blending or mixing of our orbitals. When two orbitals mix, they create two orbitals. When three mix, they create three. Okay, it results in a lower net energy, and that makes hybridization favorable. And that's when we look why we have things like 109.5 as our angle for a tetrahedral. We know that a tetrahedral is made up of S and P orbitals. Why would S and P orbitals make an angle of 109.5? They would make 90, they would make 180, but you don't think of that number. And the reason is because a hybrid orbital is created in a molecule. So the mixing of S and P orbitals yields two degenerate orbitals that are hybrids. Okay, so we have our pink and our blue comes together to make the purple, and this is an SP hybrid orbital. Our SP would align themselves into 180 degrees. Okay, and then we each have 180 degrees away from the central. sp2, these are three hybrid orbitals that align themselves in 120 degrees from each other, resulting in trigonal planar geometry. sp3 is four hybrid orbitals that align themselves 109.5 degrees away from each other, and it makes a tetrahedral geometry. Again, look at these. These four bonds, or these four orbitals here, would not have 109.5, right? We have to have this hybrid orbital to make that work. All right, and so we can see that our geometries come with general hybrid orbitals that you normally see. All right, and so let me flip over here to this, which I forgot to erase, so hold on. When we look here at this molecule, we are going to look and talk about the hybridization. So we're going to look at carbon 1. When you're figuring out hybridization, it is very simple. You give each bonding domain a hybrid orbital. So start counting at S. This is P1, P2, P3. So C1 has sp3 hybrid orbitals. Then we go on to the next one, and we have our C2. What is the hybridization at C2? We start at S, we have P1, P2. This is sp2 hybridization. Okay, again, we'll erase those. C3, we have S, P1, and P2, sp2 hybridization. Then we have C4. C4 has S and it has a P over here. So it has sp hybridization. Same with C5. sp. So essentially what you're going to do is you're going to take each of the domains and give them a letter, starting with S, P1, P2, P3. Then we go to D. And that is because, again, our hybrid orbitals, remember we would have one orbital for an S, we have 3 orbitals for a P, and we have 5 orbitals for a D. And so you count that way, and it gives you the hybridization. Okay, questions on that? You can ask Miss Lynn, or we can talk about it on Friday. All right, the next question here are our sigma and pi bonds. Okay, when we're counting. Sigma bonds are all single bonds. Okay, and one of the domains of a double or a triple. So for our sigma, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sigma bonds. Then if we go ahead and we look at our pi bonds, we have 1 pi bond and we have 2 pi bonds. So we have 3 pi bonds. Remember, a double bond is 1 single and 1 pi. A triple bond is 1 single and 2 pi. So if we flip back over to types of bonds, we've talked about sigma. Sigma bonds have a sideways overlap, and our pi bonds have a sideways, but they are not direct head-to-head. So sigma bonds are head-to-head orbitals. They are always single bonds. Our pi bonds are a sideways overlap, but again, they are above and below the plane of the bond. Okay, they are above and below the plane of the bond. Multiple bonds have 1 sigma and then 1 pi or 2 pi if it is a triple bond. So if we look at molecular nitrogen, molecular nitrogen we know has a triple bond. So what it has is it has 1 sigma bond and it has 2 pi bonds. Okay, 1 sigma and 2 pi bonds. We know that our multiple bonds are stronger and shorter than our single bonds. Okay, and that resonance is an average. All right, so the Lewis diagram of molecules of 3 different hydrocarbons are shown above. Which of the following claims about the molecules is best supported by the diagrams? All the atoms in molecule 1 lie in one plane. Now we have, again, at each place, we have tetrahedral geometry. Tetrahedral geometry we know is not in one plane. All the molecules have the same empirical formula. So the empirical formula, we have C3, this is H678, this is C3, 1, 2, 3, 4, 5, 6, and then we have C3, and we have H4. So that is not true either. The carbon-carbon-carbon bond angle in molecule 2 is close to 180. So if we look, the carbon, 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 this would be our central atom. On this central atom, we have a trigonal planar. We have a single bond, and a double bond. So this would be 3 bonds, 0 lone pair, and that is trigonal planar. And trigonal planar, we know, has 120 degrees. And the strongest carbon-to-carbon bond occurs on molecule 3. This is a triple bond. Okay, so the answer here would be D. All right, there's a lot of resources. I've also posted some on my website and in our playlist. Make sure you look at playlist 15 for this week. We are going to have a quiz on Thursday, and it will go over Vesper theory, and it will go over SAP 7, because that's the last retake in class that we need of SAP 7. So it will not be a full unit test. You do have homework over Thanksgiving, and that is a packet that you will have access to in the beginning of the week, so you can get started whenever you want. It is due December 1st. On November 30th, we will be having a unit test on all of Unit 2 and Section 3.1 and 3.2. Okay, have a great week. I will send some more videos and see you on Friday.